Our notes for this evening are pages 13 and 14, and the title is Domain and Range. So let's turn to page 13 and 14. I know normally we start on the even page on the right-hand side, but tonight I actually want to start on page 13 with this little blue sheet that you picked up that said Dixroy across the top, and that just stands for domain, which is all of our inputs, or on a graph, it's our x-coordinates. And the domain of a relation is the set of all inputs or x-coordinates. And that just means any value that we could put in for x and get out a y value as an answer is part of our domain. Similarly, our range is all of our outputs or our y coordinates. So the range of a relation is the set of all outputs or y coordinates. And that just means if there is an x that gives us a y value, then that y value is included in our range. Our notes today, I really want to focus on the different ways that we have for writing domain and range and all of the different notation that we use. So you picked up a green sheet of notes, a green sheet of paper in class today, and there we go. So if you fold that set of notes into thirds, then you can section off different parts. So I folded mine into thirds, and then I cut along the outer page so that then I had 3 flaps that I could open up for these notes. So take a minute and go ahead and section off your notes so you have 3 different flaps. So we have 3 different ways that we're going to talk about writing domain and range. The first way is using set notation, and set notation just means that we are going to write our domain or range inside of squiggle brackets, these squiggly brackets. Okay, so on the inside of that flap, I want you on the right-hand side to write that if the graph is continuous, and I'm going to flip back to our function examples and talk about what that means to be continuous. For example, this graph that has arrows on either end of the line is a continuous graph. It means that we're going to include all of those values every single place along that graph. In contrast, this graph is called a discrete graph. It is not continuous because we do not have a line connecting those points. Those are individual points. We call that discrete. So if we come back and we look at our set notation, if the graph is continuous, then inside the squiggly brackets, we will define a variable and describe it algebraically. So an example would be, let's come back and look at our graph again. For example, if we are looking here at our function that is a recursive function, this function is telling us we're starting our x values at 0, and then we're continuing with x values greater than 0. So our range for that function, if we were to use our set notation, we would say x is the variable we're talking about, and x is greater than or equal to 0. And then we close our squiggly brackets. We can also define our range using set notation. So let's come look at an example. For example, if we had a graph, and we don't have one here, so I'm going to draw in a graph that is a function. And I'm going to say we're going to start at a y value of 5. Okay. So for this function, our lowest possible y value is 5, but then from there we're going to keep going up and up and up and up, and see here we've got graph going up and up and up both directions. So for this graph, our range, our y values, our y is greater than or equal to 5. And we put that in our squiggle brackets. That is if our graph is continuous. In contrast, if the graph is discrete, so we have those individual points, we're going to list all of the inputs or outputs inside our squiggly brackets. So an example would be, let's look back at our domain and range notes. In this set that we have down here, our domain is all of our x values. So we have -1, 2, 3, and 8 are all of our x values. So inside our squiggle brackets, we would write D for domain equals squiggle brackets -3, 1, 3, and this should be an 8, not a 4. Okay. So that was our set notation. We can also describe domain and range algebraically, and we would use all of our inequality and equality symbols. So for example, our greater than symbol, equals, greater than or equal to, less than or equal to, less than, or not equal to. All of those are algebraic notation. So if we're going to use algebraic notation, we're going to use the inequality and equality symbols to describe domain and range. And I went ahead and I listed out, reminding myself of what each of those symbols means, so that if I don't remember, I can come back and I have a place that I can look. And then on the left-hand side of that flap, we're going to write some examples. So let's look back at our functions. For example, on this graph, our smallest possible x value, so we're looking at our domain. If I'm following this graph all the way to the left, I can keep going, keep going, keep going. That arrow tells me the graph is going to keep going, keep going, keep going, all the way forever. So no matter where I am on this graph, whatever x value I'm at, I'm going to have a place where I can come up and find a point on that graph for the y value. So that tells me that my x starting value is all the way down at -infinity. And similarly, if I am looking going to the right on this graph, all the way I'm having places where I can come up and find a point on the graph. That arrow tells me that graph is going to keep continuing on and on and on and on forever. So no matter where I go out here, I'm always going to be able to, for every x value, come up and find a y value for that graph somewhere on the graph. Even though it's not drawn here, it's out there. The way we would write that is looking at our x values. We would write from -infinity, less than x, less than infinity. We don't use the equal to sign when we're talking about infinity because we can't actually ever reach or equal infinity. And we would read this as x is between -infinity and +infinity. Or we could look at a graph that started at 0 and went to infinity. And that would be something like, for example, back to our recursive function where our x values started at 0 and then all other x values greater than 0 would go all the way up until infinity. So we would write that as x is between and including 0 all the way up to infinity. We can also describe our range using our algebraic symbols. So this example, where y is between 0 and infinity, would be an example for this graph here. So if we're looking at our graph, and let's go ahead and highlight our graph so we can see it and talk about it a little bit easier. So that pink line is our graph. Notice that nowhere down here with negative y values is there any place where we're going to find a point on the graph down here at negative y values. The only time we have part of that graph is when we're above the x-axis. So all of our y values have to be positive. In fact, the very first y value we have is 0. So we would describe this graph as our range is from 0 all the way up to positive infinity, because we know this graph is going to keep going, up, 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 up. So to describe that, we could have a point, an x value where the y equaled 0. So we would start at 0, less than or equal to y, less than infinity. So it's going to go all the way up until it reaches infinity. Okay. Or we could have a situation where, for example, if we were looking at, we can describe the domain and range of functions even if they are not relations, even if they are not functions. So if I am looking at this circle graph here, and let's say we knew that this was a -1 here and this was a +1 here, then I could describe the range for this function as we have points on our graph where the y value is from -1 all the way up until +1, but nowhere above that are we ever going to find a point on the graph. So we would never reach a point on the graph for any other y value. So that graph, we would describe the range as going from -1 to 1. So y is between -1 and 1. Or another example, this is our last example for algebraic notation. If we are looking at this function, we had already talked about the domain for this function a while ago. We could talk about the range. Every single point here, our range is 5. Our y value is 5. So we would describe the range for that function as y equals 5, because every single time our y value was 5. All right, on to our last notation. This is the very last way that we use notation to describe domain and range. And it's called interval notation. And interval notation uses brackets and parentheses. Okay, so we would list our domain and range with brackets and parentheses, and normally we put commas between our values when we're using interval notation. So to use interval notation, we would say for each continuous section of the graph, that means each section that we have a line connecting points together, we write the starting and ending point separated by a comma. And then I went ahead and I put this little dashed line in, or a solid line, draw something there that will help you remember that we use parentheses if a point is not included in the domain or range. And that's like in an inequality, if we draw an open circle, we would use parentheses anytime we talk about negative infinity or positive infinity, because we can't actually equal negative infinity or positive infinity. And then we use brackets when the point is included in the domain or range. And that's like when we have a closed circle and we're including that point. So the examples I would like you to write down are this example where we have this closed bracket, 2, 4 closed bracket. So this would be the example that if this was our domain, for example, then our domain is between and including 2 all the way up to 4, and it includes the number 4. So we could actually have an x value of 2, an x value of 2.1, 2.2, 2.3, all the way up until 4 and including 4. So our second example, let's say we were talking about our range, our y values. In this example, we start at 5, and we could include the point 5, and we would go all the way up to 74, but not including 74. So we could get really, really close, but we would not include 74 because we have that parentheses after it, so that's not including 74. And our last example is an example where we have 2 parentheses. So we start at negative infinity, and we are going all the way up to 3, but we are not including 3. We can't actually ever reach 3 because we have that open parentheses, and that's not including the number 3. So it goes all the way up to it, but not all the way reaching 3. So set notation, algebraic notation, and interval notation are the 3 different ways that we write domain and range. But we can also describe domain and range. So I'm going to write this on page 13. And we have a couple of different symbols that we use when we are writing domain and range. We could say that for our function of f, this symbol, the R with the 2 lines in front of it, means real numbers. So this is a way that we would write that f is mapping all real numbers onto all real numbers. So this is just a way to say that our range and our domain are all real numbers. And we can write that out in words. Or write it out using symbols, using our real numbers symbol. Okay. We can also write out, for example, if we knew that our x values were between 0 and infinity, it would be okay to write out that our domain is from 0 to infinity. But once again, mathematicians are super lazy, and I would not want to have to write all of those words if I had the possibility of simplifying it and using algebraic notation and being able to write those few symbols instead of having to write out that long sentence. That's the reason for having these 3 different notations that we use when we're talking about domain and range. That is it for the evening.